just went live, so people are popping on. And so we're doing this both on Zoom and on YouTube. So you'll see some people popping on the Zoom and some people popping on YouTube. And we'll collect the questions for you from both places and just ask.
Okay, yeah, that sounds good. Cool.
Cool. So for those of you who don't know you guys, would you like to introduce yourself?
Sure. Yeah. I basically just finished my undergrad last year, and I've been working in Google as a AI resident in the perception team. I'm in Cambridge, Mass. So yeah, and we collaborate with people at MIT, and that's how this work came up. And we've yeah. So and I've been working in machine learning for around 4 years, I think, and yeah.
And what's your relationship with this super contrastive learning paper?
So yeah, the supervised contrastive learning is something I've been working on for around 6 to 8 months at this point. We have a submission in Europe, so I'm just going to present some results from there. And yeah, but this is part of a larger effort to do contrastive learning for a large number of tasks such as images, audio, videos, and so on in a supervised setting.
Nice. And Charles, also, so welcome. Charles, would you like to tell us about yourself?
Sure. Yeah. So the regulars of the salon maybe know me, but I actually haven't given one of these salons in a couple months, so it's good to be back. Yeah. So I am a deep learning instructor at Weights and Biases. So I make educational content, including these salon talks for Weights and Biases. I just finished up my PhD at Berkeley, studying neural networks and the optimization process and the optimization properties of neural networks.
Nice. All right. Welcome, Charles. I just want to check in with you guys in the audience really quickly. Where are you guys from? Tell us what time it is, where you're joining us from, how you're doing. And you can, for the people on YouTube, you can pop it in the chat to the left of your screen. And then for the people on the Zoom, you can just pop it in the chat. Make sure it says all panelists and attendees so we all get to hear what you're saying. I see someone raising their hand. Joseph, do you want to put, yeah, exactly. Okay, you found the chat. Another note, if you have questions, please feel free to ask the questions as people are talking. Cool.
Sorry, I'm changing it to local. Give me 1 second.
So the best part of these salons is a...
So sorry, okay, I'm done.
So the best part of these salons are the conversations that happen after speakers talk. So please feel free to post your questions while they're talking, and then we'll come to you right after. And we would love to spend 10 to 15 minutes between the talks just on questions, so you get to interact with our amazing speakers and ask them the questions that you wouldn't get to ask otherwise. And you can drop these questions again in the chat, or if you're on the Zoom, you can also use the Q&A button, and Charles or I will come and get you. And with that, I would like to invite Pranay to go first, maybe.
Sure.
All right, Pranay, the floor is yours.
Share my screen. Yep.
Cool. And we can insert virtual clapping here as we welcome you onto the stage.
Okay. I hope you can see my screen.
We can.
Okay, great. Yeah. So just before I start, this work has been done with a lot of people. So Peter, AJ, Aaron, Chen, Sir and Dilip are at Google, and Philip and Yonglong are at MIT, and this has been a joint effort with them. And yeah, we have submitted this to NeurIPS, and we have an archive version available, which we will be updating as well. So the results in this talk are going to be from other contrastive learning work, supervised contrastive, and some results which are not exactly published yet, but we'll get there in a few days. So yeah, if you have any questions about those results, you should definitely ask them. Right. So basically, contrastive learning is this study where people have used representation learning in a context which is separate from the downstream task. And the basic idea which came out of theoretical work that was done by Sanjeev Arora at Princeton a few years ago was basically that you can pull samples which share class information, or they are different augmentations of each other, and hence you know that they are more similar than others together, and push samples which you expect to be different um, apart. And these could be various kinds of transforms that you could come up with, such as color transforms, crops, warping, Gaussian blurs, and so on. And all kinds of meaningful semantic information retaining transformations are useful. It also depends on your downstream task sometimes, but we can get into that later. So that's basically the idea of contrastive learning. So our goal was to understand why these work so well, and what's the basic principles which we can extract from that, and what are the use cases where this, what are the kind of downstream tasks where this works well. So this is kind of the work that came out in the last 12 months, which gained a lot of fame. Basically, there were these two papers. One was contrastive multiview coding by people over at MIT, and the other was the paper from Hinton's group, which is simpler. Both of them work in very similar ways. So what you have on the left is that you take different color transformations and you actually reduce into various color spaces, just let's just luminance and maybe chrominance, or maybe various semantic segmentations, and then you embed them using separate encoder networks, but into the same representation space. The representation space is shared, while encoder networks will be different. And you do this for a single image. So you have, let's say, 4 representations corresponding to one image, and then you try to push them together, while you try to push representations from any of these networks for a different sample apart. And so this is a completely unsupervised way of learning representations in a contrastive learning setting. Simpler had a slightly different view, where they took random data augmented versions of a sample, which was basically random crop and then color transforms, color jitters, Gaussian blurs, and they encoded them and basically pushed the representations of the two dogs together and the representation corresponding to different data augmentations of the chair together, but pushed the representation of the dog and chair apart. But this was not done using label information. Hence, they could have very similar looking dogs being pushed apart in the representation space. So um, before we go into more details, I just want to talk about how these techniques usually work. So the aim here is that the downstream task that is you evaluate on is still top one accuracy and labeling samples. So the way you do it is that you have a first stage where you actually do contrastive learning, and contrastive learning losses are actually applied in a small 128 dimensional space. So you have your encoder network, which actually gives an output of 2K, and then you actually project it down to something like 128 dimensions or 256 dimensions, depending on what your use case is. Apply contrastive losses in that space, train your network, and then you drop out the projection networks and use the 2K embeddings, that is the last layer of the ResNet in most cases, or efficient net, whatever is your encoder network. And you apply a linear classifier on top of that and try to do cross entropy training. So there's a first stage where you're doing contrastive learning, and a second stage when you're doing cross entropy learning. This is in contrast with standard cross entropy where you train end to end. And the benefit here is that these representations are independent of the label information. So you'd never use label information during contrastive learning. So the idea is that you should be able to use it for transfer learning and other downstream tasks without actually biasing your training procedure with using labels. Right. So the form of the loss that is used in such contrastive learning setups is something that looks like this. So you have the total loss over the entire batch, and for every sample in the batch, you have a likelihood term inside the log. This likelihood term comes from the exponent of the similarity between the embeddings. So Zi is the embedding corresponding to sample I, and Zj of I is a data augmented version of a given sample in the batch, and you have the similarity between them as Zi.Zji. This can be generalized to arbitrary kernels if you want to, but in most cases, since you already have a projection network, you can assume that a kernel is being learned by that projection network. And then you, so basically you exponentiate and you come up with this likelihood term. So this, what this term is, it basically says that given the batch, what is the probability that J of I is the most similar sample to sample I among all the samples in the batch. And so this is not over the entire training data set, but for like large batches, you can say that, okay, this is an unbiased estimate of the likelihood in the entire data set. And well, maybe not unbiased. It's going to be biased, yeah. But right. So you have this log likelihood term which you are minimizing. So you're maximizing the likelihood, and this is what you use to train the entire network end to end. And you use all the other samples as negative. So negative is any sample that is not supposed to be similar to the anchor. So and a positive is a sample which is supposed to be similar to the anchor, and in self-supervised losses, that's just the single data augmentation of the given anchor, right? So but why should that work, right? And there are various papers which were doing similar things. And what is different about contrastive learning? Like triplet losses have been known, and Siamese network have been known, and like a bunch of other things have been known. Like energy-based models have been famous for a very long time. So the question is that what is amazing about this contrastive learning framework? And the answer is that contrastive losses are a lower bound on the mutual information between the views of the data. So given a sample, you have two data augmentations of it, right? One of them is being called the anchor and the other is being called the positive, right? And contrastive loss is actually a lower bound on the mutual information between these two samples. So uh, what you're technically doing in this entire training procedure is using this likelihood estimate to actually maximize the amount of mutual information between the two views of the data. And note that these two views are actually created arbitrarily by you. You are either doing color transforms or you're doing data augmentation or something like that. And you can do a lot of other things. Like for example, in videos, you could actually take different frames, right? So just having two views on the data, right? And actually maximizing the mutual information between them, and you have a lower bound for that. So you have the contrastive loss that can be optimized, right? And the byproduct of that is that you can show that the self-supervised loss, when minimized, actually also minimizes some version of the downstream classification loss. So under some regularity assumptions, like your downstream loss is going to be a classification loss, and it's probably going to be a binary loss or a categorical loss and so on, you can come up with a bound on that. If you actually minimize the self-supervised loss, you're going to get some multiplicative, it's not an additive bound, but a multiplicative bound on your downstream task. So which is a good thing, because it means that what you're optimizing inherently optimizes what you care about downstream as well, which is not the case usually, right? So this is why it works, and you can look into the details of some of the work that has been done, such as the work by Bachman and the work by Aurora, and these are great reads in themselves, right? So but all of that's fine, right? The question is that we tried this before, and a lot of formulations came out before. Does this work now? And the answer seems to be yes. Sinclair basically made the claim that with a 4x ResNet 50, they are able to get as much as supervised performance, which is a great result. And there are arguments about, okay, why didn't deeper networks work, and why did wider networks work? But it is inarguable that self-supervised learning is getting very close to fully supervised learning. And uh, the question is that, can we push it further? Can we actually make contrastive learning work better than cross entropy learning, right? Because in the end, you're still only using label information in these self-supervised settings when you're doing actual cross entropy training of the linear classifier that is trained on the embedding. So you freeze the embeddings and now you're training linear classifier, but still being trained with cross entropy, right? So you didn't actually use your label information very meaningfully. You just use unsupervised part of your data. So that is where our work comes from. The motivation is that could you basically take this entire line and just push it up, right? And the formulation we came up with was just going along with the way of thinking that we have in standard contrastive learning, that you have an anchor, which is, let's say, this cute dog, and then you have uh, an augmented version of the same sample, which is a positive, and maybe you have this other cute dog, which is also a positive for this same sample, right? So, and you push away all the other samples, such as elephants and cats and so on, which is not something that self-supervised contrastive does. Basically, self-supervised contrastive will also push away this specific dog from the anchor dog, which is not a good thing, because you actually want this to be like a smooth fall off instead of like a very extreme fall off, that okay, the moment you move away from a single sample, nothing has a very high likelihood in this 2k dimensional high dimensional space. You don't want that. What you want is that it's a smooth fall off, and the fall off corresponds to the actual semantic similarity. And label information in some sense is a good measure of semantic similarity. There are better ones, and more diverse labels also help, but uh, given what we have, label is definitely something that we should use, and this is how we're using it. It's still not clear how to do this perfectly, because we had this likelihood and mutual information kind of interpretation before, and we want to keep all of those without making things more difficult for ourselves. So what we realized was that there are multiple possibilities. One clear possibility is that just take out samples which correspond to samples from the same class being used as negatives. So do not push against them, basically. And does that work well? The answer is no. It does not lead to great boost in performance. And our running hypothesis that you actually do need to pull samples which belong to the same class together. And there has been recent work which shows that there are other ways to get around this. But our way was that you actually use them as positives, in the sense that samples from the same class but which are not data augmented versions of the anchor, you pull them closer to the anchor instead of just not pushing them away, if that's clear. And the other contribution that we felt was very important in making this work was using stronger data augmentation to make sure that you don't now learn spurious correlation to labels, because that was one of the good parts about contrastive learning, that since you weren't using label information, you weren't picking up spurious correlations between your image data and the labels associated with them. So the idea was to have very strong data augmentation which gets around that. Right. So I'd just like to introduce what the loss function looks like. So the expression might be slightly hard to work with, but um, here's what it looks like. For a given anchor I, right, in the batch, you have a set of samples which are positives, which are denoted by P of I. So you normalize for the number of positives you have for a given sample. So you don't want that some losses are higher or lower because they just have more samples and more positives in the batch, because we are still sampling our batches randomly, and we don't want that it ends up that some of the sample, a large amount of the gradient comes from a few samples. Um, Right. The next part is that basically we again have a likelihood term, but this likelihood term is computed for every positive and every so for a given anchor, for every positive that exists, you compute this likelihood term, very similar to self-supervised, where you have this dot product which is supposed to be a measure of similarity, and then you exponentiate to get this likelihood term. And what we are basically saying is that we are minimizing the negative log likelihood of the sum of these likelihoods, right? And what's that's equivalent to saying that you are actually maximizing the joint likelihood uh, of all the positives given a specific anchor. So that's the distribution that we are working with, right? The other possibility is that you actually take these likelihoods, you add them up, which is basically saying that okay, you just have this conditional distribution and you're just adding all these likelihoods together, and you are going to maximize this likelihood together, right? And so basically you compute this likelihood and you keep the log outside. So the big difference when you look at the expression is that if the summation 1 by p of I is inside the log, which is this case, and or outside the log. And what our results suggest is that outside is better by a very big margin. And the insight there basically is something like this, that when you have it outside, a given positive, um, which is very far away from the anchor, has an equal contribution in the gradient as a positive which is very close to the anchor, right? But uh, that is not true for when the summation is inside the log. And you can see this from the expression, because you have these probabilities getting added up, and you have a temperature parameter here. So when this temperature parameter is actually low, which is generally the setting that we have, then one a large amount of the likelihood is actually concentrated on a few samples. So it will turn out that most of the magnitude of the gradient will actually come from a few samples in the second case, which is not optimal for training, because then you're not using your label information meaningfully, right? So this is the loss function we ended up working with. Uh, all the terms except the self similarity are in the denominator, and the numerator has the single term corresponding to the similarity between an anchor and its positive, and then you sum over all the positives. And just talking a little more about the loss function, because some people have this notion that there's something unique about this loss function, and our perspective is that while the interpretation of the loss function as a mutual information um, minimizer or maximizer is uh, interesting, that is not what is training the model. What is training the model is the gradients, and we should be able to look at the gradient and make interesting observations. So one of the interesting observations that we have been able to make is that the gradient looks something like this, where the gradient of the embedding, gradient of the loss with respect to the embedding is something like, so we have 1 by tau term, which is basically weighing the representation which are coming from other samples. So it's weighing z of p, which is the representation corresponding to the positive, or z of n, which is the representation coming from the negative. And there is a weight associated with it. The weight is proportional to P of IP. P of IP is nothing but the term we had here. So this term inside the log, that is what we call P of IP, is basically saying what is the likelihood of the positive coming from the same class as the anchor I, right? So basically what we get down to is that the gradient looks something like the embedding multiplied by the probability, and then a correction term. This correction term for the loss that we actually end up using is 1 of p of I, which says that I will correct for all of those terms equally, and the amount by which I will correct is 1 by the number of positives I have in the batch. In the case when the summation is inside the log, it turns out that this correction term is a likelihood among all positives. So for all the positives, you have a correction term which is larger for the ones that are closer to the anchor, and smaller for the ones which are far away from the anchor. This can get into weird issues, and this is why we believe that the performance is not actually very good for the summation inside the log. Right. So what do the gradients like? We haven't trained any models yet. We've just looked at what the loss function should look like. We have done some few experiments. What do the gradients already tell us? This tell us definitely that hard negative and positive mining is already being done by the model. You don't have to do it manually, which is a very good thing if you are interested in implementing and productizing these models. The second is that everybody talks about that larger batch sizes help. Well, larger batch sizes have always helped deep learning because they stabilize the gradients. But why do they help contrastive learning more than cross entropy? And the answer is that since a large amount of the gradient is determined by what is this probability P of IP, if you actually end up getting a hard negative, right, or a hard positive, that is going to have a very large amount of contribution in the gradient. So larger batch sizes also increase the probability that you end up hitting a strong positive or a strong negative for your given anchor. And we don't know of any work that has actually tried to argue it this way. And we have an analysis in the paper which actually goes through the procedures of these results and shows how you come down to this. And I would encourage people who are interested to read that and maybe expand on those ideas. Right. So the most interesting part for a lot of people, that's the results. Not for me. I like the theory more. Um, so we have amazing numbers, I would say. Firstly, we were able to get state-of-the-art numbers on ResNet 200 with both cross entropy trained with auto augment and stacked rand augment, and we were able to get state-of-the-art numbers on ResNet 50, 101, and 200 using supervised contrastive trained with various augmentations. And I'll go into details of that if anybody's interested. So, but overall, the picture looks like this, irrespective of augmentation and more complicated techniques. Supervised contrastive gets you better performance. Cut mix here is not exactly a standard augmentation in the sense that it actually mixes samples. So it uses label information more meaningfully, but contrastive learning actually does better than that. So that was interesting to me because I was surprised by that result. Um, uh, we see consistent improvement across models and across data sets. So we're better than SimClear, which is unsupervised, cross entropy, which is supervised, max margin, which is also supervised, and then supervised contrastive is better than all of them for CIFAR 10, 100, and ImageNet. Um, then this is a more detailed version of the results that we have. And so on top 5 we have a state of the art number used on ResNet 200 with the augmentation stacked rand augment. And I can go into details of what this augmentation really is later, but basically it's just a more stronger augmentation than rand augment with color jittering and blurs. And and we also have similar numbers using auto augment on ResNet 50. And the key takeaway here is that if you have a larger architecture that helps supervise contrastive, if you have more stronger augmentation for those larger architectures, even then it helps supervise contrastive. Smaller architectures can get into trouble with stronger augmentations, but um, supervised contrastive helps against cross entropy anyway. Um, right. So this is all of this is on ImageNet. The question is that the entire point of doing all of this is that can you actually generalize? So and by generalize, I mean generalize on different data sets. So we have this transfer learning benchmark, which is the VTab benchmark. We choose a small number of tasks. So what we have here is a model that is trained on ImageNet and then is fine-tuned on these specific data sets, such as CIFAR 10, 100, food, Sun 397, VOC, and you can look at details of that in our paper as well. And the key idea here is that first, that we are competitive with most of the state-of-the-art models, which are cross entropy and SimClear on both ResNet 50 and ResNet 200. But the interesting part is that permutation significance does not exist between cross entropy and supervised contrastive. And our running hypothesis there is that for classification tasks, if you're training on ImageNet, the architecture is actually more important than the technique with which you're learning, but we could be wrong about this. And yeah, we haven't seen any interesting results which suggest that this is entirely untrue. Um, and that's after tuning, right? Without tuning, you could see differences. But we did see differences on the COCO data set, and we do see that supervised contrastive does much better. And this is like a very recent set of results that Yonglong has come up with. Basically, we see that compared to other tasks. So this number is not state of the art on COCO with like larger with like other training techniques actually get much better numbers than Coco, but this is specifically comparing to other supervised techniques, and we do see that supervised contrastive does better. Um, right. Uh, we also see that we are actually much more robust to corruptions in the data set. So if you take the ImageNet test set and you actually corrupt it at various severity levels, as has been suggested by work done by Dan Hendricks, you can construct this ImageNet C data set, and we actually measure performance on that. So in the most important metric, in my opinion, is relative MCE, which measures the relative drop in performance with higher corruptions and severity levels. And we have state-of-the-art results for ResNet 200 and ResNet 50. You can also see this curve, which clearly shows that we are better than cross entropy. So the purple curve is ours in both of these cases. The dotted is ResNet 200, of course. We also do see that we are much more stable to hyperparameters. One of the most important hyperparameters in contrastive learning is temperature, which we show here. But we do see that any temperature choice between 0.04 to 0.11 is mostly getting us near state-of-the-art performance. And we are working on trying to make sure that you don't have to tune the temperature so much. Of course, we also see that even at smaller batch size, supervised contrastive continues to do better than cross entropy. And this was a question that was raised by a few people that do you think that at lower batch sizes is won't? No, the answer is that even at lower batch sizes, we do better. And this is like a 256 batch size, a 512 batch size, which you don't need TPUs or anything to train with that. And we also experimented with various augmentation schemes. So we have much lesser variation in performance with augmentations. You can change all sorts of augmentations. The augmentation used during pre-training, in the contrastive stage, you can change the augmentation used for training the linear classifier, and so on and so forth. But we do see that the performance is that doesn't change a lot. And same thing holds for optimizers. On learning rate, I would say the jury is out. Right. So uh, learning rate changes we are susceptible to, especially learning rate changes in for pre-training. So you do need to tune your learning rates for contrastive learning still. But our hope is that one day you won't have to. Right. And one of another set of interesting results is that at small percentage of data, when you actually let's say take only 1% of your ImageNet training set, but evaluate on the full test set, what is your performance? And we realize that supervised contrastive does much better. So this is top 5 performance, and we get 57%, which is compared to the 38% of cross entropy is just much better, and that holds throughout till 100. So it's a log chart on the x-axis for percentage of data. And we just think that we do better because we're learning more meaningful representations. Right. Um, there are a few downsides to contrastive learning, specifically for people who productize models, that it has a long training time. You need to train for like 350 epochs. We've often trained for 1,000 epochs as well to push performance, even though it doesn't lead to great results, but you have to do that. You can mostly get good results with cross entropy, which is state of the art if you have the right parameters in 100 to 200 epochs. So we are much longer than that. Larger batch sizes help us a lot. So if you want to get state-of-the-art performance, you want to use large batch sizes, and that gets problematic from not just computational reasons, but sometimes the network size is just too large because you're working at very high resolution images. So that's another problem. And then there is multi-stage training, and you need to decide, if you want to update your batch num parameters or not, and what's the momentum that you want to use. So it's just another set of parameters that you introduce. So that's definitely a very big downside of contrastive learning. And just very quickly, kind of things we're still working on, bunch of things, and other people should also try these things. That's generalize the supervision for contrastive learning. No reason to just use ImageNet labels. You can also do out of distribution detection, and maybe even classification free out of distribution detection, if that makes sense. And building stability to small perturbations in input data, that's something we're working on. And learning representations from multimodal data, which is learning similarity between text representations and images, text and videos, videos and speech. All sorts of combination exist, and people have already started doing this. I saw a few papers around. which are coming out since this went up on archive. So yeah, I think very interesting. And yeah, of course, there are other contrastive learning techniques which have worked really well, and that is there's the MoCo paper, and then there is right, there's the DeepMind paper as well, and BYOL and so on. Then they have shown that if you use momentum encoders and memory, interestingly, then you can work with very small batch sizes and you can make things work. And while some of that work has been increasingly focused at unsupervised or self-supervised, we do believe that using label information would give you state-of-the-art performance when combined with those techniques. So we are trying a bunch of those things, but yeah, the people who are definitely productizing their models, they should look at if they want to try things like that. Right. So I think I'll stop here, and I'll just take a bunch of questions.
Nice. That was really good. Thank you. I have a question to get us started, and I'm sure Charles has a bunch too. Uh, so you talked about how your technique does better with larger batch sizes, but
Yeah.
also most people don't have the compute resources if they have a big model to use large batch sizes.
Yeah.
What's your advice for people to use self-supervised, supervised contrastive learning in that
Right.
scenario?
Yeah, I think memory is definitely your friend. So if you can actually keep, so the way memory works is it keeps a few scale
Oh,
representations.
sorry, I think your audio is being a little
Okay.
weird.
Uh, can you hear me now?
It's like breaking like that. Kayla, do you have uh, any advice on how to fix it?
I don't. Maybe just pause your video for a second. It might just be a bandwidth issue.
Yeah, sure.
Stop video.
Sorry about that.
No, it's okay. Can you hear me better?
Better, yes.
Okay. Okay, let's just try this for a couple of minutes. Okay. So, right. So basically what I was saying was that memory is your friend there, because what memory allows you to do is keep a few scale representations around and you can contrast against them. So that's like a pseudo larger batch. The main problem with that is that since your representations are stale, when you're in the early stages of training with large learning rates, you can be really out of sync. But there are trade-offs that you can come up with. So memory is definitely your friend. And other there are I would say that uh, people have even tried keeping the entire data sets representations in memory, and that is doable for because and that's the reason why the representation over which you apply the contrastive loss is like 128 or 256, so that optimizes your memory. So that's one good reason to actually keep those small back. Yeah.
Cool. And if people can start dropping their questions in the chat, and also the folks on YouTube, I know you're like 30 seconds to a minute behind. So just if I wasn't clear, please start dropping your questions in the chat. Charles, you had a question.
Yeah. So really cool talk, really interesting stuff. The contrastive learning approach is one that I'm really excited by, and it's cool to see them like people continuing to push the envelope there. So first, you mentioned that just for general contrastive learning, there's this interpretation of maximizing mutual information between views of the data. So just to make sure that I understood that right, you mean maximizing the mutual information between your latent representations, right?
Yeah.
And you achieve that basically by pushing those together and then pushing the other ones apart.
Yeah.
Exactly. These like whatever your negative examples are. So
right.
There's like, in my mind, that immediately brings up these like positive negative sample algorithms that people use for like wake sleep algorithms, right? The way people train maximum likelihood models, like Boltzmann machines and things like that.
Yeah.
So is that is that more than an analogy? Is there a direct connection there? I wasn't able to figure that out.
Yeah. We haven't figured that out as well. Like I wouldn't say that there is a direct system there, but yes. So more intelligently sampling your positives and negatives and actually making sure that your data views are constructed intelligently If by that I mean that you make sure that there is not a very large amount of mutual information between those views, so that the when you actually maximize the mutual information between those views, you actually end up retaining only the semantic information. That is definitely a very strong part of contrastive learning, and we do think that pushing on that helps. Even though random data augmentation is like a close proxy for that, there is more work to be done on that front, I believe.
The other question that I wanted to ask was, outside of the image setting, do you expect this contrast, like how well do you expect these kinds of contrastive learning approaches to work? For two reasons. One is a lot of image classification tasks basically involve these kinds of like texture and pattern matching things that maybe don't transfer super well when it comes time to do segmentation or depth mapping or something else with images. And then second, outside of like using images for your task at all, we're relatively limited in the kinds of augmentations we can apply to something like natural language processing, where it's somewhat difficult to come up with a reasonable data augmentation that maintains semantic meaning. So like, I don't know the literature very well on this. So like, do you know examples where people have done this before? And do you think, is your intuition that this will spread really nicely to these other domains?
Yeah. So segmentation is definitely something that the same backbone that it can be used for classification can be used for segmentation. So segmentation is something that can be handled. Other ones, it's not so clear. People haven't shown these things. But moving to non-image data, text is definitely hard because data augmentations are difficult. But you can come up with sampling procedures which construct your batch interestingly, so you don't have to do any data augmentation. Because technically, see, if you don't have any data augmentation, even then contrastive learning does work because it is still pushing samples from the same class together in another class apart. And so for text, intelligent sampling helps. Audio is a signal. You can perform very interesting data augmentations on audio signals, so I'm not that worried about audio. There has been work which actually is like basically the equivalent of ImageBot, which shows that you can actually learn similarities between text and images, and there they do use image augmentations. So I do think that contrastive learning would be able to extend to such settings.
Yeah, so you mentioned, so text classification, you still have this nice class label that helps you figure out which things are similar and which things are not. But maybe something like machine translation, it might be difficult unless you have access to, say, multiple translations of the same sentence that would allow you to maybe do data augmentation that way.
Yeah, no, for sure. Yeah, for machine translation, it's not very clear how to make that work because, but yeah, I mean, some people have the perspective that why do it because basically already what we have with transformers already works. So, but yeah, I mean, I don't have a very good answer for that.
Someone in the comments. Oh, wait, Charles, were you done?
Yeah.
You can keep going. Someone in the comments asked, can you apply this to deepfakes? Because they're working on deepfakes and excited about trying this technique.
Um, I do think that it's worth a try, but we haven't done it, so I won't say yes because I don't want to be held liable for that. Right. Statistical regularities and irregularities is not something that I expect contrastive learning models to be very good at because strong data augmentation actually normalize for that. So I would actually expect that they would just learn to ignore a lot of statistical irregularities. And if deepfakes are actually using those statistical irregularities, then it's possible that we're not able to handle that. And yeah, so I won't say for sure that it would work.
All right, someone else.
I did have actually another question.
Yes.
Yeah. So, are you familiar with slow feature learning? It's like it's sort of a pre-deep learning approach. The idea is, if you have like video data and you want to learn like basically do image pre-training, what you do is you learn you learn representations such that the features don't change from frame to frame, or they change as slowly as possible from frame to frame. So you have a term to keep the entropy non-zero, right? But then you also have a term to keep the covariance high. So this slow feature analysis idea has been used by a couple of deep learning type approaches, but it seems like a version of like contrastive learning without the contrast, right? It's basically just positive samples. But there might be some interesting ideas in that slow feature analysis world for contrastive learning.
Yeah, I think I agree with that. I do think that there is a very big space for contrastive learning where what you do is you take video data and you have this graded notion of a label. So you have a graded notion of a similarity, and then you try to optimize for that. So you can basically have a weighted form of the contrastive learning. And I think people are trying this. I know of a few teams who are trying this. So the hope would be to see some slow moving and some fast moving features which automatically come up because of the structure of the loss.
Cool. Someone else in the comments asked, could you talk more about the augmentation techniques that you tried and what makes supervised contrastive learning stable to these augmentations more so
Yeah,
than
let
other
me,
ones?
right. Yeah, let me try and pull up something. Okay, so basically uh, broadly the augmentations we cared about was auto augment, rand augment, um, stacked rand augment, and sim augment. So going through them, auto augment is basically the strategy which is trained. So you have to apply two augmentations, and you decide the magnitude of those augmentations and the order of that augmentation using a policy gradient learning algorithm which optimizes for the top one accuracy of ImageNet. Rand augment works slightly differently. You have a controllable parameter, and then you sample your pair of augmentations that you want to apply randomly. And the idea is that if you tune this parameter, which is like the magnitude of the augmentation correctly, you actually even beat auto augment. So basically, the idea is that even if you learn a policy, you can just actually randomize it and get the same thing. So if you don't have compute, you should just use rand augment. Um, then what we did with stacked rand augment was that we actually, and this was Longlong's contribution, that he basically figured out that if you take Gaussian blur and color jitters, and after applying color jittering, before applying color jittering, you actually do a rand augment. So before you actually apply the color jitter, you actually do rand augment, then you do a color jitter, and then you do a Gaussian blur, right? But this rand augment is applied after doing the cropping. So the order basically goes cropping, rand augment, color jitter, Gaussian blur. Then this is a much stronger augmentation and much more useful for contrastive learning. So that's basically what the stacked rand augment is. And sim augment is basically something that the Hinton paper introduced. The right, and what they did was color jittering, Gaussian blur, random cropping, flips, and we had added something else on top, which was warping, which actually just shows 4 points and actually just warp the image. So the second part of the question was that, and I don't know if I got this correctly, that why do these augmentations work well for contrastive learning? And
Yeah,
right,
yeah, yeah,
yeah,
essentially.
yeah. So the idea basically there is that uh, augmentations are supposed to spread a single data point in the representation space. So what that allows you to do is like you have like a denser epsilon ball in a high dimensional space for every point. So now this contrastive learning setup, what it allows you to do is not just that you're pushing away single points, you're actually pushing away this density, and that is more meaningful. So that's one good reason to use augmentations. The question is that why would one augmentation work better than the other? Um, the answer is not clear. We do think that denser is better. So basically, it's like this in this 2K space. How much can you explore using your augmentations? So the more orthogonal systems you have in your augmentations, the denser this epsilon ball is. but right. But this is basically an analysis, and it's not very grounded. Like we don't have a lot of experiments to back this up, but this is more intuitive in the geometrical space.
Gotcha. And is this also related to why supervised contrastive learning is stable to corruptions in the ImageNet dataset and to hyperparameters like temperature and stuff?
Right. Yeah. So we do believe that yes, since we're doing a much more meaningful representation learning system. So like okay. So the point is that even if you use the same augmentation for cross entropy and supervised contrast are still better. So that means that it's not just the augmentation, but it is the fact that you're never able to pick up on spurious correlations between your um, labels and your representations, and that's just like a property of the cross entropy function. That the cross entropy function is going to try and best and minimize the loss, right? So
Yeah.
it will try to pick up spurious correlations, but since you have this dense ball and you're pushing these dense balls around, there's no notion of why you should pick up any spurious correlations, because it's not just about projecting this ball using a linear plane into the right class. Now it's about actually pushing away these dense balls and the two-K space.
Interesting. Cool. I think those are all the questions that I saw. Charles, do you have? Oh, wait, there's more. Um, Interesting. Someone said they want to start with AI and machine learning. They have a strong background in Python. At what stage should they be taking interest in subjects like contrastive learning? What should be their path? This is an important question, I feel like, because all these Coursera and and Udacity courses do such a good job of like teaching you the fundamentals, but how do you go from there to like, picking up interest in something specific like you?
Yeah. Okay, I can describe the way I did things. Ian Goodfellow's book is, I think, a very good plus place. His book, it's available online freely, and you can just read that book and build intuition, and then just start reading papers. So like but yeah, you need to re-implement things on your own. So you need to have like a goal in mind that okay, you want to maybe re-implement very difficult GAN paper or contrastive learning paper or something, and then read through books and papers to get to a stage where you have the end-to-end understanding of each step and why you're doing it.
Gotcha. That makes sense. Cool. I feel like we've gone a lot more over time, but the questions are amazing, so I kept going. Thank you so much, Pranay, for coming.
So,
If you want, you should totally do an AMA in our Slack community, and you'll get a lot more questions there. And we'd
okay,
love to.
sure.
Thank
Okay,
you so
all right,
much for. Oh wait, someone has another question, but we'll get to them later. Yeah. Thank you so much for coming.
no problem. Yeah, I'm just gonna stop sharing my screen now.
Cool. Uh, All right. So next up, we have one of our regulars, and Charles is a deep learning engineer and instructor at Weights and Biases. He's one of my favorite colleagues, and he is going to talk about alligator pairs and random variables. Charles, welcome.
Great. Yeah, so thanks for the kind introduction, Lavanya. I added a little bit to this talk at the end. So it's not just alligator pairs and random variables, but also stochastic gradient descent. This is a collection of things whose names do not actually describe the thing that they claim to describe. So I want you to imagine what you picture in your head when you hear the phrase alligator pair. And actually, before I go into this talk, just to be clear, so this salon, we bring in people to talk about research. And then in addition, I spend a little bit of time in each salon talking about some of the fundamental mathematical ideas that go into machine learning and presenting sort of intuitions and ideas around them to sort of, give something for people who are just starting out on their journey into machine learning, and then also something for the experts. So so hopefully you've taken the time while I was explaining that to picture an alligator pair in your head. Perhaps you were picturing something that was, the shape of a pear that was covered in alligator scales, or a pear that was eaten by alligators or something like that. So an alligator pear is not any of those things. An alligator pear is an avocado, which is neither an alligator or related to alligators in any way, nor is it a pear. It's very, very different from a pear. So I've got helpful pictures and diagrams so that in case you don't recall what alligators, pears, and avocados look like, but you can see that there's like some slight resemblance between these things. There's no inherent connection. Now I'd like you to picture something corresponding to the phrase white ant. So white ant, what you've got in mind is probably an ant that is the color white. And that's actually very reasonable, but a white ant is neither white nor in fact an ant. So that's a picture of a white ant on the right side. It's a termite and it is brown. The same color as, regular ants. So some, for various reasons, these names have been attached to these things, despite the fact that they aren't natural. They don't come about sort of the way you might expect. This kind of regrettable nomenclature is also a problem in mathematics and machine learning. Really, most of the time in math, combinations of words work like you'd expect. So if I tell you that I have an abelian group, if you know what group and abelian mean, then you could say, oh, that is probably a group that is also abelian. And you would in fact be right, but not always. There are a lot of things that are in math where the names of the individual components of the name refer to something, but the combination refers to something quite different. And these exceptions are often where people get tripped up and confused. And I recommend sort of leaning into this confusion and trying to understand what are these other words, the words that go into this compound word, what are their definitions? And then what is the definition of the overall thing? Why are these different? How are they different? And by sort of leaning into that confusion, we can actually really enrich our understanding. If we just sort of, try and shy away from this confusion, we're actually, I think, going to end up missing lots of important pieces. So the primary example that I want to work through on this front is on random variables. So random variables may sound like a variable that is random, and in some sense, that's the way they behave, much like the alligator pear is kind of like, it's almost like a pear, but it's got this alligatory skin. But they're mathematically, it's not like an abelian group. They are not variables that are random. They're actually deterministic functions. And so we're going to go through the typical definition of random variables and see how understanding this definition and recognizing how and why it's different from the intuitive definition helps us better understand the things we can do with random variables. So this example actually comes from this famous quote from this book, Probability and Introduction by Samuel Goldberg. That's a probability textbook that mentions that these alligator pear and the white ant are similar to the random variable. So that's where this quote came from. This is a solid introductory probability book. I think it's a bit old, as maybe indicated by the quality of the font. So there's maybe better stuff now, but it launched this phrase into this idea of the weirdness of the definition of the random variable. So random variables are a lot easier to exhibit than they are to define. So if somebody was like, what's a random variable? It's a lot easier to just list off like, oh, you roll a die and a number comes up. You don't know what it's going to be. There it is once you've rolled. How much rain there's going to be tomorrow. You can maybe predict that better than a dice roll, but famously, weather reports are not perfect at predicting whether there's going to be rain and how much there will be. The number of tweets in the next millisecond, depending on the moods of a bunch of various influencers, this number can go way up and way down and can be difficult to predict. The fourth decimal place of the time right now, that one gets used as a random variable in computer programs all the time. And a famous random variable people who do machine learning and deep learning have encounter is their next gradient update. It'd be great if we knew our gradient updates without having to calculate them, but they behave somewhat randomly, and we have to calculate them to know what they are. So these are all examples, but they aren't a definition. So the standard definition is a kind of a strange one. It first asks you to imagine a collection of all possible universes. So this gets given the very fancy capital omega letter, and then asks you to define a function that, given a universe, spits out the outcome of some event. So imagine it's a scientist with a microscope that can look into, or a telescope that can look into universes, alternate universes, and say, oh, in this universe, the die came up a 1. In this universe, the number of tweets was 3,000 in the next millisecond. So spitting out the outcome of the event. That function is what we call a random variable. So there's some minor restrictions on this function, but unless you are a hardcore analysis kind of person, you aren't going to accidentally come up with one that makes this break. So don't worry about it too much. So just in picture form, we've got our collection of all possible universes on the left, the collection of objects of type universe, and then we define a function that takes an object of type universe and returns an object of type integer or type Boolean or whatever. So in the case of the number of tweets in the next millisecond, it's a function that takes in a universe and returns an integer. So that's written in the bottom right-hand corner in this sort of type notation. Number of tweets is a function that goes from universes to integers. So maybe there's 6,000 in a couple of universes. Maybe there's 10,000 in another universe. That's the one where, Donald Trump just tweeted in the last second, and the other ones is one where that didn't happen. Maybe there's one where there's 0 tweets in the next millisecond because Twitter went down, right? So these are all the different possibilities. This is where the sort of randomness in the number of tweets in the next millisecond comes from the fact that we don't know which of these universes we're in, you might think of. So the same thing could be done for the next gradient update. It now returns floating point numbers. Maybe a lot of the times our gradients are very sparse, and so we get 0 gradients. But then other times we get, relatively small numbers like 10 to the minus third, and, all possible numbers maybe come out of all these different universes in which our process of sampling the next batch draws a different set of elements to go into our network. So number of tweets and next gradient are properly considered functions, but we call them random variables because we want to manipulate them like variables. We want to be able to add them together and multiply them and apply functions to them and things like that, the same way we work with things that we actually know the value of. But in order to actually define them, we needed to define them as functions. So now we're going to go through how, using that definition, we can understand what lets you add and multiply and divide random variables. But first, a quick summary. So we've got our universe on the left-hand side. This is, maybe the whole collection of universes is omega. We've got our outcomes. Maybe it's all real numbers on the right-hand side. And then our random variable, our random real number, is x, which is actually a function that spits out real numbers. So I think I've already talked a little bit about why this matters, so maybe the slides become a little bit redundant. But the biggest thing that I want to point out is that strong command of this unintuitive definition will help you when it comes time to extend this definition and work in places where your intuition might fail you or lead you astray. So the first thing is that it's clear how to define new random variables from old ones based off of this definition. And the way we define a new random variable based off of an old one is maybe we want the number of tweets in the next millisecond, but maybe we want to say whether that number is above 10,000 or below 10,000, right? Because that's what's going to cause higher load on our server, right? So normally, if we want to check if the number is above or below 10,000, we we pass it to a function that returns true or false if it's above or below that cutoff. And so we can't pass a random variable directly to a function because a random variable is a function. So if I try to ask, is this function bigger than 10,000? Python or whatever my language is going to throw an error. What we do instead with functions is we compose them. So I've represented that here by drawing these sort of like arrows for the functions and putting them tip to tail. So something comes out. Let me do a little pointing here. Something comes out of this function. This is an outcome of, say, number of tweets. It goes into our function, say, is bigger than 10,000, and out comes something else, a different type, possibly, like a Boolean that says true or false. And this defines a new random variable that we introduce this notation for, which is kind of a strange notation. It says, instead of saying, oh, this is f of x of something, which is how we'd normally do it, we write it as f of x. We pretend that our random variable is a normal variable that can go into functions, and then we rewrite it this way. But when we write it that way, we really mean something like this. So this has the utility of making it easier to write things once we understand what we're talking about, but it can kind of trip people up when they're trying to learn these definitions for the first time. We can also get rules for the distribution of f of x based off of this, and it's much easier to understand where they're coming from looking at a diagram like this than from the baseline definition. So if you've learned maybe the Jacobian rule for a Jacobian determinant rule for changes of variables, it comes out of this. And then this is where we get to define our algebra of random variables, where we get to take our algebra that we normally use. We can add numbers together, multiply them. We can do it with random variables also. So the idea is if we have two random variables that both operate on this same collection of universes, then we can define their sum by, say, applying both of them, getting now two possible outcomes. An outcome of x and an outcome of y, maybe the number of tweets in the next millisecond and the number of tweets a second from now, and then we can add them together. So the way that this plus works is it takes these two, this is actually your normal plus. It takes two arguments and adds them together. So like the dunder add function in Python is maybe what you should picture, a function that takes in two things and returns the sum of those two things. And we can define now the sum of x and y by composing these two arrows together, by first getting two outcomes, then adding those outcomes together. Now, this is a new map, which this combination of these two maps is a new map that goes from universes to outcomes, but now it's computing a sum instead of computing just the outcome of one or the other. So this is a new random variable. So this works for times, this works for minus, this works for more other possible things. It's also the case that we can do it for data types. We can make random lists, we can make random dictionaries, random tuples, all the kinds of data types we work with in computer science. Using the sort of reasoning with diagrams like this, we can define what it means to, say, take a pair of random variables. And this actually leads to a really powerful approach for understanding these kinds of data types and for understanding what it is we're doing when we're combining these arrows together. And lastly, this is where it's really valuable, is we can even define random functions. So just as random variables were actually these, deterministic functions, random functions are actually deterministic higher order functions. So now what's happening here is we're looking into a universe, and that universe is spitting out not just a single number, but a function. So I've represented that here by this tiny arrow. So notice that this tiny arrow is much smaller than these big arrows. This is maybe bad notation, but bear with me. So we look into our universe, it spits out a function from A to B. So we write that now with a little f instead of like the capital X that I was using in the past that represented a variable, or capital Y or something like that. So this is now a function that returns a function. So in computer science, we think of those as higher order functions. So it's like a lambda in Python. It can take an argument and give it to another function. So when we're mapping, so when we get this random function out, we then, if we want to get a random variable, a single value, we pass an argument to that function. So turns out you can represent the argument that goes into a function also with an arrow. So this guy is takes a function that goes from A to B, gives it the argument A, and returns B. So this is something that maybe you would use a lambda for in Python. And then this whole thing we write as f applied to the value A. And that's evaluating a random function at a point A. And so random functions, you may not have come across them that much, or may not have realized you were coming across them that much. But random functions are actually part of some of these really important recent models for understanding neural networks based off of the neural tangent kernel and the Gaussian process model of neural networks. Gaussian processes are random functions, and neural networks with random weights are also random functions. And that people tend to get tripped up when they try and understand these things because their understanding of random variables is maybe is incomplete because they haven't gone all the way to the through and understood this definition thoroughly. So I had a little section here on stochastic gradient descent, but actually I think I want to keep the focus of the talk just on that random variables material, and maybe we'll cover this stochastic gradient descent stuff later. But you'll find if you look kind of really closely, stochastic gradient descent is kind of none of those things. But we're going to skip over, I'm going to skip over that and take any questions from the audience about this material.
I would actually love for us to go over the stochastic gradient descent stuff if you want to.
Okay, maybe just a quick pause. I'll give it maybe a few seconds for the YouTube people to catch up. If anybody on Slack has questions.
I have a question. So you said the sum of two random variables is also a random variable. And I'm wondering, does this randomness increase when you combine two random variables? And also, what happens to the underlying distribution that you're pulling random variables from?
Yeah, that's a great question. So one thing that didn't come up that much in this was what are the distributions of these random variables, right?
Yeah.
So that there is a way to calculate these distributions. It's basically, it's called a push forward. You take the distribution and you push it through the function. And then you watch how things get stretched and scaled. So there's a definition involving integrals and things to get you what that actual expression is. So for adding random variables, if the two variables are independent, you convolve their distributions. So you literally take the distribution and you flip it around and then slide it by multiplying and summing, the same way you do a convolution in a neural network. Gotcha. So there's a way to see where that comes from, but that basically falls out as the trick that you can use when you're adding two independent random variables. If the variables are dependent on each other, all bets are off, and it can become like basically arbitrarily difficult to figure out what their distribution is. But in general, I think you can't say that the variance either goes up or goes down when you add two random variables. They usually go up. Like the baseline case is that they go up. But say I have two random variables. One is defined as a coin flip that gives me +1 and -1. And the other one is defined as like, check that same coin, but if it comes up heads, give me the opposite answer. So now if I add those two variables together, they're always 0. So the variance is gone. So it's now deterministic. So you have to be a little bit careful about making sort of general statements, but most people think of adding random variables as increasing randomness.
Gotcha. That makes it a lot more intuitive. Also, does it break? Is there any point like when you're creating functions of random variables, that this paradigm breaks and the result that you get from these functions becomes meaningless because there's so much randomness, or does that not matter?
Yeah. So so what I would say is like, yeah, you can compose functions together. You could take, and people in fact do take things as complicated as neural networks and treat them as random variables or random functions. And there are many, many functions lined up together. You can do arbitrary combinations of random variables. They do, I mean, if you're combining things that are independent, what you find is that you end up, you lose lots of structure. So like the central limit theorem says, if I add a bunch of independent things, the thing that comes out is Gaussian. And so it doesn't matter. There's random matrix theory that says if I take a really big random matrix and all the entries are independent, the resulting eigenvalues always follow a specific distribution. So there's a general thing that says, whoa, if you're combining a bunch of independent random things, what you get is actually something that's less complicated than all of its pieces. So those are the main examples I would think of. The only way this paradigm breaks down is there is this restriction of measurability on functions that's important for anybody who's trying to come up with, I don't know, like a Banach-Tarski paradox kind of thing, or trying to, come up with some really weird function that returns, non-measurable functions are actually pretty hard to construct. So I'm not going to come up with an example right now. Which should tell you just how like broad this thing covers. It's the kind of thing mathematicians and analysts really worry about. But when you're doing machine learning and working with random variables, it basically never comes up.
Gotcha. All right, cool. Let's see. I know Kyle had a question. So Kyle, if you want to jump in and ask, there it is.
Yeah.
So go ahead.
Yeah, it looks like Kyle asked the question in the Q&A. Yeah. So when we talk about neural networks as random functions, is this still the case once the network has undergone training? So to think of a neural network as a random function, you usually think of the weights as being random, right? So you're doing like a Bayesian neural network. So you're saying you're saying I started off with a distribution over possible weights. Like my prior told me my weights were somewhere between -1 and +1 uniformly, or they're from a Gaussian distribution. And a fully Bayesian approach to neural network training never drops that randomness. It says, oh, each gradient update tells me to move this Gaussian around, usually make it much, much skinnier and put it around a specific value. But I still keep a distribution. And so then the neural network remains a random function in that to evaluate it, you would have to draw a specific set of weights. And that specific set of weights is drawn at random. But what we do normally, right, is we just draw some specific thing and then we use the gradient updates to change them, and the network remains a deterministic function all the time, unless you use dropout, in which case that network is also a random function. But I think that doesn't come up quite as much, the idea of thinking of dropout as something that makes your network a random function. And so I would say that it's really more the idea that if you keep a distribution over weights, then you get a function that is then your neural network is a random function, and this leads to this Gaussian processes view of neural networks and their loss surfaces that has been making a lot of waves in the theoretical community in the form of the neural tangent kernel over the past year or so.
What if you pulled the nodes that you drop out from a distribution? Then you would remove the randomness.
So let's see. If you're pulling the nodes that you drop out from a distribution, and those nodes are random, then the neural network is going to be a random function. I think so. So it seems like one other, some other people want actually to go through the SGD example. So we might as well just do it. So. Okay, so stochastic gradient descent. It's a common algorithm, and yet it is one that this alligator pair problem hits pretty badly, especially on the gradient and on the gradient part to a lesser extent on the descent part, and still a bit on the stochastic part. So I have another little motivation slide. So Voltaire, who was an influencer in the 18th century, wrote in his History of Europe, the agglomeration which was called and which still calls itself the Holy Roman Empire, pictured here on the right, was neither holy nor Roman nor an empire. So it wasn't holy because it actually spent most of its existence fighting with the Pope, which is not very holy. It wasn't Roman because it was, you know, in Germany, which was never really part of the Roman Empire, and nor were the people in there ever Romans. And it wasn't really an empire because the entire thing was basically a huge mess of princes and bishops squabbling with each other, and it never really behaved as a coherent unit. So my update to that is that this algorithm, which was called and is still called stochastic gradient descent, is neither stochastic nor of a gradient nor a descent method. So the first part, stochastic gradient descent, is not a descent method. A descent method for minimizing a function f is a method such that if I evaluate the function on each consecutive iterate of that method, so the method produces theta's parameter values over time t from 0 to capital T or from 0 on out. A descent method says the next value of the parameters will give me a lower value for the function. And SGD only promises this on average. SGD can in fact go up. It doesn't in fact descend. It goes up sometimes. Anybody who's looked at a neural network training curve has seen this phenomenon occur. And gradient descent, where you don't have the stochastic part, almost does this, but it only does it if you have a small enough step size, or if you're like shrinking the step size. So even gradient descent is actually not a descent method. So the reason why this is important is because if you actually go and you look at the analysis of descent methods, how do we prove they converge? In what cases do they converge? What causes them to break? The theoretical analysis and the practical, the theoretical analysis is just very different for descent methods and for something like SGD. They're, you know, completely different actually when you look at the details of the math. And then the practical behavior is also different. Seeing values go slightly up in gradient descent, and especially stochastic gradient descent, par for the course. Seeing values go up for a descent method means you implemented it wrong. So this is, you know, these are very, very different things when it comes time to debug or to analyze. The second one, and this is perhaps the strongest leg I have to stand on in this rant, is that stochastic gradient descent does not use gradients. A gradient for a function f is a function nabla f that satisfies this relationship here, which basically says if I evaluate the function at a certain, if I want to know, oh shoot, there's a little bit of an error here. This nabla here should not be there. So ignore that guy. If I look at the function's value at some point epsilon away from a point theta, then it should be approximately equal to a linear function times how far away I went. So that's what this inner product here says. So this applies for scalar valued functions that take in scalars, vectors, and matrices. And importantly, this is true for every choice of theta. But stochastic gradient descent, as we use it in ML, works perfectly well for functions that don't have gradients everywhere. So I have two examples, on the right-hand side, both of which are very popular in machine learning. One is the rectified linear unit on the top, and the other is the absolute value, which in high-dimensional cases, this would be the L1 norm, which shows up as a sparseness penalty in sparse activations or sparse parameter regularization schemes. So these functions get used, but if I try and ask, is there a function here that is a good linear approximation of this function? It breaks apart, actually, it's easiest to see here. There's no good linear approximation to this function at the point 0, right? I could get this side perfectly right, but then just completely whiff this side, or I could do the same on the other. So this function does not have gradients everywhere. What it has everywhere is something called a subgradient. And more broadly, when you want to go to high dimensional cases and you want to go to functions that are non-convex, it's something called a subdifferential. So these subgradients are actually super, super important for convex analysis, the study of convex functions, which is where all the ideas in optimization come from. All of our ideas of how do we optimize functions, how do we find the lowest values of functions, even when we apply them on non-convex functions, on generic functions, we use ideas that came from convex optimization and convex analysis. And so one of those central ideas is the subgradient. So it's not only a central, it's actually what's really being implemented in something like TensorFlow when they compute gradients for you. It's also something that is a key theoretical tool. And the fact that it's being used is completely swept to the side by the name gradient descent. And then lastly, and this is the weakest leg of my 3-leg argument against stochastic gradient descent, but bear with me. A stochastic method is one that generates or uses random variables. And we just talked about the definition of random variables. One thing that, depending on your definition of randomness, really the things that go on inside of a computer are at best pseudo-random, which means they appear random to a person who's not looking very closely, but they are in fact entirely deterministic. If you were to run your code again in the exact same setting, then the code would produce the exact same output. So the way that this is managed is that there is a seed number that determines the behavior of your code. So if you set a seed, the behavior of stochastic gradient descent becomes entirely deterministic. So if I want, I can actually recreate the exact training process for a network if I know the seeds for the pseudo-random number generators that went into training that network. This is very different from an actual stochastic algorithm that has actual access to random values. So one that's, say, queries the behavior of this. There's a famous qubit. I forget who measures it, but there's a famous quantum system that produces honest to God random values. And if somebody checked that qubit before running stochastic gradient descent and used that in order to run their algorithm, you'd never be able to guarantee you'd recreated their training process. So this is important for a couple of reasons. And the biggest one is that it's important for debugging. We can actually, because the algorithm is deterministic, we can recreate it and we can interrogate it at a later point in time, the same way we can any other deterministic algorithm in a computer. So we can do testing, we do unit testing, we can do searching through and printing statements, doing print statements to pull out variables and looking at what their values were. We can understand what happened during algorithm with perfect clarity, no stochasticity needed. Verifying the behavior of a stochastic algorithm with tests is really, really hard. And it's actually quite lucky for us that our stochastic gradient descent is not so stochastic that it cannot be made deterministic. And another actual argument is that you can remove all the stochasticity from gradient descent by just, if you pick a fixed order for the values to come in, and that order is not, say, all the instances of one class, then all the instances of another class, all the instances of a third class. If you just pick that order to be some permutation of the inputs, you drop all the stochasticity. You don't have to randomly load batches and keep flipping coins to decide which elements go into your gradient descent and which ones don't on a given batch. You just go through it in order, but that order is just, it just can't be a really, really dumb order. And this is actually a weird behavior of gradient descent that people don't understand very well. That version of it does just as well as stochastic gradient descent. And there's basically, once you've once the order of the data set is set, there's no randomness. The algorithm is completely deterministic. So I have here, now a change.org petition, a call to arms to rename SGD to APSD. So hopefully folks will join me in referring it to instead as approximate pseudo-random subdifferential descent. Approximate descent being how we get around the problem of descent not being what we're doing. Pseudo-random to emphasize that this is not a stochastic algorithm, and subdifferential so we actually name the thing that we are using rather than calling it a gradient just because that's easier. So that concludes my pedantic and completely unnecessary rant about the nature of stochastic gradient descent.
That was amazing. A bunch of people said in the comments that you are hilarious, which we agree with. There's a question in the chat if you want to take it.
Yeah, so Nicola V asks, what are some pros and cons of making the training process deterministic by fixing a, quote, random seed? So the biggest con is that there are some times that you really do want the network to behave randomly, right? Like actually, so I focused on the fact that if you wanted to uncover some bugs in your implementation, you want to be able to recreate a given run in order to make sure that that you could figure out what caused the problem, right? But you could run, if you just fix a single random seed, then you might actually miss that your algorithm doesn't have the random behavior that you would expect. So sometimes we can do things like take averages or expectations or otherwise remove out the effect of randomness by considering a large number of examples. And often we do want our algorithm to behave differently when it gets different values for the seed. So that would be, I think, the biggest con for making the training process deterministic by fixing a random seed. The other thing is that when there's actually been some recent papers that say that if you treat your random seed as a hyperparameter, you can get better performance on your validation set. So it's important that you make sure not to do that on the test set because now you're really, really just overfitting. But there are aspects of maybe some initializations of neural networks for certain kinds of problems are actually better than others. So instead of just trying multiple runs with the same hyperparameters, you might include a single random seed. Maybe there's an interaction between where you start on the loss surface, where you start your neural network, and what your learning rate is, or how much dropout you do, or whatever other your atom hyperparameters or whatever. So that, that's a somewhat controversial new approach in machine learning. People worry that we're really starting to just chase a few percentage points of accuracy, but that would be a con for setting a fixed random seed. You can't do that.
Do you want to take the one in the Q&A section?
Yeah. Kyle asks, is there a relationship between the fact that SGD isn't truly a descent method and the effectiveness of early stopping when training neural networks? So not directly. So for folks, early stopping means that you sometimes want to stop training earlier rather than running forever. Right? A naive analysis of optimization would say the longer you can run your algorithm for, the better you will do. Even for stochastic gradient descent, even for non-descent methods, longer tends to just mean better. Because basically all our algorithms are motivated by calculus, which works when things are infinitely small or run for infinitely long. So, but the reason for early stopping is actually that we're optimizing the wrong thing. We're optimizing the training loss, whereas the thing we really want to optimize is the test loss. Or actually, the test loss isn't really what we want to optimize. What we really want to optimize is our social or business outcome of, increasing dollars per ad or decreasing the number of deaths to heart disease in the world. And so, the training loss that we're actually optimizing is very far away from the thing that we want to make good. And so early stopping is one of those things that you include in order to try and do better on the thing that you don't have direct access to. So it's a little bit separate from this point about descent methods. But I think that's a little bit of a tricky thing. As somebody who basically, did my PhD in optimization, optimization is not the most important part of making your neural network actually do the thing you want it to do. It's maybe the most fun part for people who like math, like me, but it's actually, you're going to be missing a lot of the important context, whether it's out of distribution and test performance, or the overall, impact of your algorithm and its deployability and things like that.
This is not related to your talk a lot, but you alluded to how the loss function is so far removed from what we're actually trying to optimize, which is the business objective. So do you have advice on bridging that gap that people, especially in the beginning of their careers or even far along, should be thinking about, and how to close that gap?
Yeah, I think in the beginning of your career, I think the thing that most people are missing is an understanding of the technical aspects of machine learning. And so I think that at the beginning of your career, you should really focus on understanding those things better. Because to be honest, whatever you were doing when you weren't learning machine learning probably gave you the right, the sense for whatever it is that you're going to apply it for. Maybe you did I did a biology undergrad, so when I go to do machine learning applied to biology contexts, I have context that helps me understand what the real goals are and what the failure modes are. So at the beginning of your career, I think you should really focus on getting these technical aspects right, because they can bite you, and when they do bite you, they bite hard. But for more people who are more experts and they're at the point they're actually deploying models, I would say the only solution is like careful thought, like maybe spend less time on fiddling on with your hyperparameters and more time thinking about what will this model look like when it's in production. Get models to production as quickly as possible, unless you're in a security critical regime like medicine. And then learn from what happens when the model is deployed with sort of continuous sort of testing strategies to ensure that the model is not starting to fail completely. There's a lot of people who are doing work in fairness and ethics in AI. This is another aspect in which our loss, which encourages us to do well in the aggregate, can cause us to do things that we actually did not want to do, which is to fail for groups that are underrepresented in the data set. So to look out for that, among all the many other things that fairness and ethics researchers have pointed out as problems with machine learning algorithms. So yeah, those would be, I think, my pieces of advice for people who are more who are out there deploying. But to be honest, my expertise is in the actual understanding of the mathematics and the pipeline of training the model, and so that's where I have the best advice to give.
Nice. Another thing that you could do to bridge the gap between business objectives and the loss function is to capture more things that are closer to the business objectives in your training data, and make sure your training data captures all the features or all the variables that affect your business objectives, and then you'll optimize the right things. And somehow in this convoluted process, you'll optimize your business objective. Yes, Charles, you were saying something?
Oh, no, yeah, definitely. Quality of the data comes absolutely first. This is something that I think gets lost on folks with an academic background like me, where the data set is some fixed benchmark usually, and the idea that we need to think very carefully about where the data came from and what that collection process implies about what the test distribution is that this thing might be optimizing. That's an important aspect that gets missed a lot in academia, in part because it's really hard to say anything satisfyingly academic about it.
Yeah, that makes sense. All right. Do people have any more questions? I'm going to give you guys 30 more seconds to ask Charles, or Pranay is still online too, to ask them any questions that you have. And until then, Charles, do you have another talk for us planned, a part 2?
Yeah, I'll be at the next salon for sure. I've got a couple of possible ideas, maybe something about the singular value decomposition. I think that's what I'll cover.
Nice, nice. All right. So our next salon, we tried this 9 a.m. time to get some of our European friends to join us because they always say that the 5 p.m. time normally doesn't work for them. And we're going to do some analysis on what time works better for most people. And we'll be back in 2 weeks, either on Tuesday at 5 p.m. PST, or we'll be back on Thursday at 9 a.m. same time in 2 weeks. So I guess we'll see you then. Thank you, Charles, and thank you, Pranay. Thank you, Kayla, for helping. And thank you, everyone who joined. We really appreciate it.
Take care.